At the heart of understanding complex vector flows is the concept of homogeneity, which acts as the genetic code for how a field behaves when you scale your perspective. Imagine a field where, if you double your distance from the center, the strength of the field changes by a predictable factor. This consistent scaling is what defines a homogeneous field. A fundamental mathematical principle, known as Euler's theorem, provides the bedrock for this study by proving that the radial rate of change for such a field is simply a reflection of its inherent scaling power. This principle transforms abstract calculus into a predictable geometric constraint, dictating how energy or flux is distributed across a field's geometry. When we modify these fields by multiplying them by their own radial projection, we uncover a core identity that describes how the resulting field spreads out, or leaks, through space. This measure of spreading is not arbitrary. It is governed by a precise relationship involving the field's scaling power and the number of dimensions in which it exists. As you move from a flat two-dimensional plane to a three-dimensional volume, the field's tendency to spread becomes more significant. The final result reveals that the total leakiness of this modified field is a fixed, linear scaling of its original radial strength, determined entirely by adding the scaling power to the dimensionality of the space. This abstract theory finds a powerful physical application in the electric field of a point charge. In our three-dimensional world, a point charge follows an inverse square law, which translates to a specific scaling power of -2. While a standard electric field has no spread in empty space, applying this specific mathematical modification unlocks that spread. For a point charge in 3 dimensions, the resulting flux density becomes exactly twice the value of the local electrostatic potential, turning a vacuum with zero spread into a space that effectively glows with non-zero flux. The geometric intuition behind this transformation is the idea of softening or flattening the field. Normally, a point charge's influence decays extremely rapidly as you move away. However, the mathematical operation of multiplying the field by its radial projection effectively buffers this decay, reducing its steepness. Visually, this results in a transition where a rapidly weakening field is transformed into one where every vector maintains a constant length regardless of its distance from the source. This flattening of the radial decay is the direct geometric consequence of the shift in homogeneity, demonstrating that the way a field scales is a fundamental law governing the distribution of forces throughout the universe.